I had been using arrays like this with the students that I'm tutoring, and they seemed to understand. They could write the numbers if I presented an array. They could label it like 7 times 3 and then write 7 times 3 is 21. And it seemed that they understood what they were doing here. But come to find out, when I asked more questions, several different examples of questions that I asked that they had no idea how to answer because they didn't understand that 21 is the number of circles in that array. They knew when you see an array like that, you count 7 down, 3 across, and then you write the problem, 7 times 3 equals 21. But they did not know that that meant there were 21 circles in that array. And I never would have known if I hadn't asked them some other thing. This was one of the ways that it was revealed to me that they didn't know that the answer to the multiplication problem is also the number of squares in the array. I was showing them square numbers, and I had arrays that were arrays of square numbers, and then I had just blocks, and I had them experiment to see if they could make a square array out of the blocks and then identify which of the numbers could be called square numbers because it was possible to make a square array. And then I asked them, how can we get square numbers without going through the process of playing with the squares to see if it's possible to make a square array? And they didn't know. They were stumped. So I showed them the pattern. Look, we have this one's 2 times 2, 3 times 3. We have 4 times 4. So what number would give us another square? And they didn't know. And then when I was trying to illustrate for them that we could break a problem like this break the 16 up into 10 and 6, and I actually had 16 squares to make the array, and that 16 across, but we could do it in pieces, the 4 times the 10 and the 4 times the 6. And they did not know, well, that's a different problem, is what they thought. Now you're solving a different problem. That's not 4 times 16. And I tried to convey, but it's the same number of blocks. And they thought, yeah, what's that got to do with the math problem? Like they didn't get a connection. So I figured this is too abstract for them. And these are kids who it looks like they know what's going on because they know to write the multiplication problem and put the answer, but they're really not conceptualizing what they needed to conceptualize. So I tried like 4 different things that didn't work, and then I found something that did work. So I want to share that. So here is what finally worked, and I'll walk you through how I did this so you can make your own Jamboard if you want. I went in here. First thing I got was an egg carton. And just chose one. And I pointed out that this egg carton is 2 by 6. And the number of eggs it holds is 2 times 6 is 12. And I'm working with 4 different students, all very bright, 3rd grade. And they had light bulbs go off like I had no idea. So then we did some arrays where instead of a square, we use this egg. Here's a better one. And we just duplicated this and we made arrays with eggs. And then I had them pretend that they are going to be an entrepreneur innovator and they're going to design an egg carton that holds 12 eggs, but it's not 2 by 6. So what different egg cartons could you design that would hold 12 eggs, same number of eggs, but it's going to be rectangular because that's required for shipping purposes and for putting on the shelves. It's going to be a rectangle and it's going to hold 12 eggs, but it's not going to be 2 by 6. And that they understood. And then I went and they could do anything I asked them. And it sunk in that the number of eggs in the array is the answer to the multiplication problem that you make when you see the array and count the rows and columns. And then I made others I had more flexibility when I used cupcake pans, or muffin pans. Because muffin pans actually do come in a bunch of different sizes and shapes. So we did some muffin pans, and I had cupcakes, and we arranged them. And then when I got to what I finally wanted to do, and they worked after we played with the muffins and the cupcakes, then they were able to understand this, where I said, you own a big restaurant, you've got a great big oven, so you can put any size cupcake pan in that oven. And you've got a huge cupcake pan with 7 rows and 16 columns of cupcakes. How many cupcakes fit in here? If we draw the line here, and you've got 10 here and 6 here, then they understood it's the same number of cupcakes that it was a minute ago when you were looking at all 16. And they could do 70. I mean, it was a light bulb went off, and 42, and then they can add those numbers together, and they know how many cupcakes. And then I went on and had them write it as 7 times 16 equals, this was after we did a bunch of these, and it had sunk in, is parentheses 7 times 10 plus 7 times 6. And I told them that is the distributive property, which they like those big words, and that this is what is represented. It's like you got your big cupcake pan that's 7 by 16, and you're going to draw a line here in the cupcake pan and count the cupcakes that way, 70. And they understood it, and they could do it finally. So I just wanted to share that. Previously, they had not been able to do a problem like this, and I didn't understand why, because they understood the arrays, and they knew to write a multiplication problem and the answer, and I thought, well, why can't they do this? But after we did the cupcakes, then they understood, and I told them the inches, the area is like the cupcakes. The area of that rectangle is 16 inches squared, and if it was a cupcake pan, there'd be 16 cupcakes. So they're just asking, what other cupcake pan could you design that would hold 16 cupcakes? And they totally finally understood this. And before they were clueless, and I couldn't figure out why. But I think it was just too abstract to have the array just be an abstract concept instead of eggs or cupcakes. But making it concrete like that, they got it then.